In this video, I'll talk about calculating the coefficient of determination, also known as R-squared, for a simple linear regression model. So we'll use the same example we used in the last video, and this time we'll do a couple more calculations that will allow us to calculate R-squared. So let's see. So first of all, let's look at this number. No, let's look at this number. Okay, I've labeled this SSE. This is the sum of squared errors. So what exactly does that mean? Well, we calculated y hat last time. So that was the predicted value of y using the regression equation. So for example, 60 plus 5 times 2 comes to 70, and so on. So we can do that for the 10 observations in our data set. We could look at the difference between y and y hat. So 58 minus 70 comes to minus 12. 105 minus 90 comes to 15, and so on. So these are known as the residuals. So they're the difference between the observed y value and the predicted y value. Some of them will be positive, some of them will be negative, and that refers to the fact that in the graph here, some of the observed y values are above the line with a positive residual, some of them are below the line with a negative residual. If we square those residuals, we can also think about the residuals as representing errors in the model. So we could think of this as squared errors, and then this is the sum of squared errors. So that's what this number is down here. SSE means sum of squared errors. It's really the sum of squared residuals, but it's often referred to as sum of squared errors. What about this number here, SST? That stands for total sum of squares. And that comes from here. So what is this measuring? This is measuring y minus y bar. So here's y minus y bar. Let's remind ourselves what that was again. That was y minus the mean of y. So we could think of this as if I was to draw on this graph a horizontal line at 130, the average of y, so right around here. If I was to draw a line right along there, and then, so if I look at right here, so this would be on that horizontal line at y bar. And then now if I looked at the difference between y and y bar, it would be from here to here, or from here up to here. And then for this point, it would be this distance. And for this point, this distance, and so on. And then on this side, from here down to 130, that would be y minus y bar. So we could think of that horizontal line at y bar as being what our best estimate of y would be if we didn't know what x was. So if we didn't know about this association between sales and population, and all we were trying to do was to guess what sales would be, and all we had was these numbers, our best guess would just be the average. So that's what y minus y bar represents. It represents, if you like, the error that we would have if we just used y bar to estimate y. So we can square and add those up as well. That comes to 15,730, and that's called the total sum of squares. Okay, the sum of squares due to regression is the difference between those two sums of squares. So 15,730 minus 1,530. And R squared is calculated as the ratio of the sum of squares due to regression over the sum of squares, the total sum of squares. And the idea is, let's imagine that the sum of squared errors was 0. What would it mean for the sum of squared errors to be 0? Well, that would mean all these points would have to lie right on the line because there's no error, and we're adding up a bunch of zeros squared, and we get 0. So the sum of squared errors is 0 if all the points lie along the line. If that was 0, then sum of squares due to regression would be the sum of squares total. These two numbers would be the same if this was 0. And then r squared would be the ratio of one number to another number where the two numbers are the same. It would be 1. So that would be one extreme. R squared is 1 if the points are exactly along a line. Let's think of another extreme. Let's suppose we had just a random jumble of points here, no pattern whatsoever, and the regression line was flat. In particular, the regression line was right at y bar. Okay, so that would mean the sum of squared errors and the total sum of squares would be the same. Because either way, I'm measuring the distance to y bar and then squaring and adding up. And in that case, the sum of squares due to regression would be 0 and r squared would be 0. So that's another extreme. R squared is 0 when there's no linear relationship whatsoever. So R squared 0, no linear relationship. R squared 1, perfect linear relationship. And so that kind of tells us what R squared is measuring. It's measuring the degree to which we have a linear relationship here. Often this is described as the proportion of variation in y that's explained by the regression model. And it ranges from 0% if there's no relationship, no linear relationship, all the way up to 1 if there's a perfect linear relationship. And the other thing to know about R squared is it's often expressed as a percentage. So rather than 0.9027 here, it might be expressed as 90.27%. And so the way we would interpret this number is to say 90.27% of the variation in y can be explained by this simple linear regression model. That's not to imply there's any causal relationship between x and y. It's simply we're observing a linear association, and 90.27% of that variation can be explained by the model. We can also calculate the correlation between x and y using r squared. If we just take the square root of r squared, we clearly get r. But you have to be a little bit careful because sometimes a simple linear regression model can have a negative slope. If there was a negative association between these two variables and it went this way instead of this way. And so the correlation always has the same sign as the slope estimate. So that's why in this formula, there's an extra piece at the beginning that looks at the sign of this number, and r is given the same sign. Okay, so let's see if we can find where r squared is on the Excel stat output. So I'll just fit the model again using Excel stat. And let's okay that. We'll see if we can find where r squared is on the output. Okay, so I'll scroll down. There's the equation that we saw before. And actually it's higher up. So it's here in this table here that says goodness of fit statistics. There it says r squared, and there's the 0.903. If we look up here, 0.9027 to 4 decimal places, and that's what we calculated here, 0.9027. Okay, so that's how to calculate the coefficient of determination, or R squared, in simple linear regression.